latecomers will sit with us. I was just thinking with all the latecomers are coming on the latecomers. Yeah, we should come down forward.
Hello, Jay.
She can have. I don't need
Oh, this went back to sleep. She has to do the password again. Okay, we'll do it just when you are ready to start. And I think then she can stay on the stage. We did not have her. She has to come again to unlock. So at that time she can then she can stay. We'll when we start. Then she doesn't have to do up and down.
It's walking up and down is not an issue, but
No, because again it's got a lock, no? So unfortunately.
yeah.
So then you can sit here once you come. हाँ मैडम को लगे हाँ ठीक है हाँ ठीक है सर शी कम्स ऑल्सो फॉर मी इनिशियली दिस माइट विल वर्क ठीक है ठीक है उनको लगाना और उनको दिखाना बाद में बट PDF चल रहा है मेरा उसमें तो पता नहीं चलेगा सो ओनली व्हेन शी स्टार्ट्स यू कैन डू So maybe you can come up one last time and see. Then don't have to do that.
There's a chair right here. No, not there.
Sit on the ground. Thanks. You sit here, no?
No, I'll sit here.
Anvish, we can start, right? Yeah. So, good evening and welcome all to this special lecture, Bimla Buti Memorial Lecture. A few words about Bimla Buti. As you know, in our exercise the other day, in the interaction workshop, we already learnt a little bit about her, maybe something more now. So, she was born in Lahore, which was part of integral India, and had her early education there. After partition, the family moved to Delhi, and so Bimla ji completed her higher education in Delhi. Her father's unstinted support enabled her to pursue research. She went to Chicago, and her supervisor was Professor Chandrasekhar, whom now in the Astro course you all have learnt about Chandrasekhar Limit. Bimla ji herself was one of the most distinguished physicists, globally acknowledged for her fundamental contributions to understanding of chaos. Internationally known as an authority of nonlinear dynamics, her work found applications in widely varying plasma systems, including astrophysical plasma. She is the first woman physicist to become Fellow of Indian National Science Academy. She founded Plasma Science Society. She worked with many organizations, Delhi University, IIT Delhi, NASA, but she spent most of her time at PRL Ahmedabad. She was known for a strict discipline in her way of work. She received numerous awards and honors. Not all are here, just a glimpse of few. She got Vikram Sarabhai Award for Planetary Sciences, INSA Venu Bappu Award for Astrophysics, Professional Achievement Citation Award of University of Chicago, US Medal of Fundamental Contributions in the Physics of Nonlinear Waves and Chaos. She was a fellow of various academies, national and international, and she also received a Lifetime Achievement Award, R.D. Birla Memorial Award from IPA. She emphasized the need for promotion of women in science. She's featured as an exemplary role model for many young scientists, especially women. And you can see some of her pictures. She was also director of ICTP Plasma Physics School from 1985 to 2003. Her message to one and all, and is really very important, is don't give up. In the first edition of Vigyan Vidushi, she gave a special lecture, and that's available to you on the YouTube. Please go through it and you will find this again, don't give up. This is a very important message. After her retirement from PRL, Dr. Buti instituted the Buti Foundation and initiated a number of awards through scientific institutions and societies. She got immersed in philanthropic activities, and the Buti Foundation information you can find on the webpage. As you know, the Vigyan Vidushi Physics and TIFR are, Vigyan Vidushi is supported from Buti Foundation, so VV team and TIFR sincerely thank Buti Foundation for their generous support to the program and to the Bimla Buti Memorial Lecture in particular. This is the third lecture in series, and today we have Professor Sumathi Rao with us to give this lecture, and she will be, it's my honor to introduce her. She's been a role model for me and many of my friends because, you know, was always there when we started. So Sumathi had received a PhD in particle physics from State University of New York, USA, Stony Brook, as many of you have heard. After postdoctoral positions at Fermilab and University of Wisconsin-Madison, she joined the faculty at the IOP Bhubaneswar. Later, she moved to Harishchandra Research Institute, where she worked till 2021. And after her retirement, she moved to ICTS, where she is currently a senior visiting professor at International Center of Theoretical Sciences, TIFR. Over the past 25 years, she has guided numerous PhD and MSc students. Her work has focused primarily on quantum condensed matter physics. She has played a leading role at national level in developing the application of field theoretic techniques of condensed matter systems. Her work has contributed to areas at the forefront of modern condensed matter physics, including low-dimensional system, topological phases, quantum Hall effect, anyons, and fractional statistics. She was also among the initiators of the IUPAP International Conferences on Women in Physics. I think she's a part of the first team, if I'm not mistaken. Yeah. And has been an active participant in the global effort to improve the representation of women in physics. She was instrumental as one of the members of the team who set up the Gender in Physics Working Group in India. She's a fellow of Indian Academy of Sciences, National Academy of Sciences India, and was recognized as an outstanding referee by APS among many numerous achievements and awards she had. She was elected as a fellow of American Physical Society in 2022 and a member of the World Academy of Sciences in 2026. She remains actively engaged in mentoring, outreach, and particularly encouraging young students to pursue research in physics. We are indeed fortunate today to have her with us because they're also running a parallel summer school program in ICTS, but we are very grateful that she found time to come here and share her exciting guidance, gave us some exciting guidance, share also some of her story. So she's going to sing a carol today, an Anyon carol, Anyon past, present, and future. Over to you, Sumathi.
Thanks so much, Vandana, for such a fantastic introduction. I hope I can
Yeah, I need to close this.
do justice to what you, the way you
Sure
said.
you will. I have not covered everything.
Yeah. pointer.
This is the pointer and this is the slide change. You can see.
The pointer. Thank you. Today I'd like to talk about, first let me start by thanking Vandana and the entire team of the Vigyan Vidushi team, I don't know who else is involved, for inviting me to give this talk. I'm really very honored to do so. And what I would like to talk today to you about is say something called an, sorry, is it on? Is it on? Can you hear me? Sorry, I didn't realize it was not on. Yeah, so what I would like to talk to you today is about the Anyon Carol. I mean, I took this title from this Christmas Carol by Charles Dickens, who talks about Christmas past, Christmas present, and Christmas future, right? So it's like that. I want to talk about Anyon's past, Anyon's present, and Anyon's future. So that was the reason for choosing this as a title. I also wanted to start by saying that as Vandana already mentioned, Professor Bimla Buti is a role model for all of us. And I didn't know her particularly personally, but she has definitely had many firsts to her credit, so we knew of her. And first Indian Woman Physicist Fellow of the INSA, APS, many things, the awards which Vandana already mentioned. She was the director of the plasma physics at ICTP from 1985 to 2003. And that's where I remember meeting her, because we used to go to ICTP fairly often, and she was a role model over there. And the last time I met her was in this, there was a gender and physics meeting called Pressing for Progress in 2019 in Hyderabad. And we had a felicitation for her 86th birthday. And that's when she gave this talk. So, okay, with this background, let me start with what are anyons. I'm not sure many of you know what these are. You would have heard of bosons and fermions, right? And all elementary particles that you know of would be either a boson or a fermion. Like electrons, neutrinos, quarks are all fermions. Photons, gravitons, gauge bosons, W bosons, Higgs bosons are all bosons. And it's true in nature or in three dimensions, three space, one time dimension, that all particles are either fermions or bosons. But in the condensed matter system, you have things which are called emergent particles, quasi-particles. And they need not always be fermions or bosons, they can be more exotic. And particularly in two dimensions, there are emergent quasi-particles which behave neither like fermions nor like bosons, but instead intermediate between them. I will give you more about, explain what exactly these anyons are. But I want to start by saying that when I started studying anyons in the 1980s, that time I was doing, actually it was high energy physics, and I was doing theoretical field theories and so on. It was an intellectual curiosity and an exotic mathematical possibility. Because so let me start, maybe at this time I'll give a brief foray into my own career in physics and how I moved from one field to another. So my basic background is that I grew up in Hyderabad and Baroda, which is now Vadodara. And I finished high school in Baroda. And I was interested in puzzles, detective stories, and things like that. And since I was academically good, I was thinking of whether to join engineering and medicine or something. That was what everybody did in those places, except in West Bengal. Good students did not normally go into sciences. And, but I was lucky that I was encouraged at home to, we grew up with books and we were not discouraged from studying, which is not always common, that I realized later on when we went to any other states and so on. I took the NSTS exam and got selected, and that was what gave me the boost to do science. And when I see you people here in this summer school, it reminds me of the science talent summer schools that I used to, were there for us in those times. But I also remember that in 1975, when I attended my first summer school in BITS Pilani, there were 40 boys and 8 girls. And the summer school was a month long, but I only survived 2 weeks. And if there are any of you who are scared and who have come from small towns, let me say that this happens to all of us, right? Because at that time, I was only one from Baroda. There were others, many were from big group from Delhi, Bombay and all that. But it's difficult when you're alone. I went home after 2 weeks, unfortunately. But from the 3rd summer school onwards, I regularly attend. I did not take advantage of this and other opportunities, but I would like to tell you all, please do take care of the opportunities. But also I want to tell you, for any reason you miss an opportunity, don't worry, life will give you other opportunities as well. Okay, so that's something you should all remember. Do try your best. Yeah, so I had my PhD I got from Stony Brook in 1983, and my PhD was in particle physics. It was on neutron, anti-neutron oscillations. I don't expect you to know what these things are, and grand unified theories, which are not even so popular anymore. But it's just that Maxwell unified electricity and magnetism. And then at that time, Weinberg, when we went in 79, there was a Nobel Prize for Weinberg and Salam because they unified electroweak theories. So in the early 80s, the expectation was that there could be a unified theory of strong, weak, and electromagnetic theory. And so that's what I worked on, grand unified theories. Now the people who are interested in these kinds of things work on string theory because you also want to include gravity, right? I did my postdoc years in Fermilab, and that's when I started working on something called a topological Chern-Simons theory in 2+1 dimensions, which was more as a toy theoretical model. And in fact, the abelian version we had did a non-abelian model, but we had anyons, which was in an appendix in our paper at that time. It was not our focus. But I didn't know at that time that that would start my lifelong career in physics. So lifelong, all my life I'd keep coming back to anyons, that's what I mean. Love affair with anyons. I came back to Institute of Physics in Bhubaneswar in 87, and this is something that many of you may also face, that if you get married to another physicist, you will have these problems of commuting marriages, that you may not get jobs in the same place. So those are things that you have to live with. But fortunately, I was lucky. Many people, this is the stage at which many women often have to stop doing what they love to do. But since I didn't have the pressure from family, at least I could manage to continue. And then in 1995, a new institute started in Allahabad with Professor Mani. And that's where both Ashok and I moved. It was a new institute, it was a starting institute, so both of us could get jobs there. So most of my working years have been spent in Allahabad. It's an institute called Harishchandra Research Institute, which some of you may know of. And that's where I spent. And then we moved to Bangalore. So my research interests in the mid-90s, I switched to condensed matter physics, which was a little difficult in the beginning because my contacts abroad were all in high energy. So I had to start from afresh. But this ICTP was a good place where we used to go, all of us, many theoretical scientists. And because those days, to learn about new things in physics, there was also not enough money in India to travel abroad, to travel to places and so on. Not only for me, for anybody else. So there's ICTP being an associate helped, and since the trip was fully paid, and we learned many things. Internet and email also actually came later than that, so we didn't even have those ways of getting to know what was going on. So I got interested in spin systems and then in fractional quantum Hall effect. And one of the reasons I got interested in this condensed matter system called fractional quantum Hall effect was because a junior of mine, Jainendra Jain, from Stony Brook, he had written a paper which got very famous, so we all looked at it. It sounded very interesting, and that's how we got into it. So there are many different ways that you get into whichever interests you. I mean, you don't know which way the path you will take. So this is what started, as I said, my lifelong affair with anyons. And I wrote a review article on Anyon primer in 1992, which is used till today. So now we have anyons in various systems. They appeared in the quantum Hall systems in the 1980s. I don't know if any of you have heard of these things now. People are working on called topological quantum matter. There at least are names. In the 1990s, anyons are there, and spin liquids. And most excitingly, in recent times, there are these things called Majorana modes. You might have heard about something called the Majorana or topological quantum computation. So those things are used in topological quantum computation. So this entire field of anyons has become extremely exciting and for research now. You have anyons in Moray systems and engineered materials, and there are many, now it's not just a theoretical toy, it's actually been seen in many experiments, which I'll talk about. So what I want to say is that yesterday's abstraction is tomorrow's technology. So you can have novel theoretical ideas, and sometimes they can really lead to future progress. You don't know which way the field will change. This is not something we could have predicted when we started working in this area. So work in whatever excites you. You never know where future progress might lie. Right? So anyons, the basics of now anyons. As I said, all elementary particles are either fermions or bosons. And the simplest generalization of bosons and fermions you can think, you know what bosons are, that if you exchange two particles, you get a plus sign. And if you exchange two particles, you get a minus sign, that's a fermion. Right? And now you can think of what happens if there's a complex phase when you exchange two particles. Right? This was introduced in 1977. So why is this possible? If you think of exchange as an adiabatic process of taking one particle to another, right? Then if you think of it as just, you can think of what happens if you exchange it twice. You take a particle like this and bring it back to itself. You take a particle like this and bring it back to itself. Then if you double exchange it, does it mean you've come back to the original case, or you haven't? If you think of the relative coordinate between the two particles, if you do a double exchange, you've taken it, the relative coordinate goes to minus r goes to minus r, and then for a single exchange, the relative coordinate makes half a loop. If you do a double exchange, the relative coordinate makes two loops, right? Now, if you in 3 dimensions, if you form a loop by double exchange, you can take the loop off the plane and shrink it to a point, right? So a double exchange in 3 dimensions is like no exchange, because you exchange it once, you exchange it twice, and you've come back to the same configuration, right? Because what I'm trying to say is if you take it like this around, or you can take it like this around, right? What do I mean? In 3 dimensions, it doesn't even mean something to take one point around another, right? You can do it in many which way. So there is no, the relative coordinate can always be shrunk to a point. Whereas in 2 dimensions, this is not possible. If you're exchanging 2 particles on this thing, if another particle is there, without going through that particle, it will always tell you how many times you can go around it. You can go in this way, you can go in this way, but you can count the number of times you go around the particle, right? So there is a difference in 3 and 2 dimensions. So this distinction is that the removal of a single point makes the space multiply connected. You can count number of times that you go around in 2 dimensions. And so this is why you can get anyons only in 2 dimensions or 2 plus 1 dimensions, 2 space, 1 time dimension. So particles in 2 dimensions this is mathematical, classified in terms of the braid group and not permutation group. That's not important. You can just think of it in terms of these pictures. You can count the number of times you go around the part, right, from one to the other. And yeah, I can, if I have 4 particles, I can go take one around 2, 2 around 3, and so on, right? So these are all these various paths which are possible. And there are only 3, you can exchange 1 and 2, you can exchange 2 and 3, you can exchange 3 and 4, you can exchange this way or you can exchange this way, you can have inverses, right? So it's important point is that you can count number of times each particle goes around the other, right? So for bosons and even for fermions, once you've exchanged twice, you can forget that you've exchanged it because it's come back to the original position, right? And for anyons, the entire history is important. And that is why if you take a system of anyons, you'll have to keep track of how many times each of the particles have exchanged with every other particle. So that makes the problem, if you have a system of anyons, it's very difficult to calculate its ground state or anything theoretically. So it leads to many new phases, phenomena, because even the fact that something is a bosons or fermions, there are differences. One leads to superfluidity, right? Superconductivity if you have bosons. If you don't have that, it has all the things that you get in materials depend on whether particles, their underlying particles are fermions or bosons, right? You've heard of Bose condensation, right, and things like that. So that will happen only for bosons. For fermions, you have something called Fermi liquid theory, right? So this is where actually topology enters quantum mechanics. The number of time particles winds around another is a topological quantum number. And as I said, it depends on the space-time, dependence of space-time. When it was proposed, it was just a mathematical curiosity, but it was drastically changed when it was realized that it could exist in real condensed matter systems. So I'll give you a very quick model of what is a physical model of what is an anyon is something that you can think of a charged particle moving around a flux, right? And you think of 2 such things going around each other, right? The model of an anyon is like a charge with a flux, and the reason I'm saying it that way is because this charge can see the flux due to this, magnetic field due to this. This charge can see the magnetic field due to this, and the reason that you get this phase is precisely because there is an Aharonov-Bohm phase, that when you take things around one another, there is an Aharonov-Bohm phase. So you can just think of it as each of the particles seeing the magnetic field of the other particles, imaginary magnetic field, right? So that's a physical picture model of an anyon that you can have in your mind. You can think of anyons as carrying little flux tubes. You can shrink this to a very small thing. You can shrink this in the z direction also and think of it as a point-like thing. But what is to be remembered is that every anyon carries a charge and a magnetic field. That's the way you have to think about it. And these things actually existed in a phase in nature called the fractional quantum Hall effect. Again, how many of you have heard of the quantum Hall effect? Integer quantum Hall effect, you all know. Fractional quantum Hall effect, you've heard? Okay, the integer quantum Hall effect is something that you know, right? That if you put a magnetic field and you have a current in one direction, then the conductance forms plateaus, right? Naively, you would have expected classically for it to be a straight line. That's the classical expectation. But they actually form plateaus. And the conductance quantization is very highly quantized to a very high degree of accuracy. And that is something which is very surprising because you are actually measuring the conductance in a real material, right? And that has impurities, it's done at different temperatures and all. But the accuracy is 1 part in a billion. And the reason for that is because there is something called topological protection. And I can't go through the theory of how you get this. It's a very interesting theory of how you can understand this in terms of Chern numbers and so on, the conductance quantization. But here all I want to tell you, okay, give you as a semi-classical explanation. You can think of, if it's in a 2D plane, you can think of the electrons forming orbits, right, in a perpendicular magnetic field. But at the edges of the sample, it can't form full orbits. but on one edge it has to go in this direction, on another edge it has to go in this direction. So the edge motion is what is called, can only go in one direction and not in the other direction. So if I can think of a current going this way, there is no way for it to backscatter. There is no channel through which it can backscatter, because the channel through which it can backscatter is physically very far away. So even if there are impurities here, it has to find its way around and just go through. So quantum mechanically, if you solve it, you can see that there is only one-way motion at the edges of the sample. And that is the reason for this extraordinary quantization. That's one way of thinking about it. The fractional quantum Hall effect, I'll just have to tell you that in much stronger magnetic fields, you can get conductance at fractions of E squared over h. And the idea is that due to strong electron-electron interactions, the effective quasi-particles in this 2D electron gas are now anyons. They're not electrons anymore. And because of that, you'll get, if you have 1/3, the exchange statistics is 1/3, you'll get plateaus at 1/3. If it's at 2/5, you'll get plateaus at 2/5, and so on. So it depends on what kind of anyons are there in the picture. And this is all something which has been seen. And there's a very famous wave function called the Laughlin wave function, for which he got the Nobel Prize in 1990s, which can be understood as if these particles, electrons, each of them have some kind of a flux tube attached to it. And so you can think of this as an anyonic wave function. What is really interesting is that these can be seen in experiments, which I'll talk about later. So now this was all anyons past. Now let's come to anyons present. And the main important thing that has happened in recent years, in the last 5 years in fact, is that people can now make anyon colliders. You've heard of CERN colliders and things with protons and electrons and all. Using these edges of the quantum Hall system, they can actually make anyon colliders. They can make a dilute beam of anyons from the fractional quantum Hall edges, make them collide with each other. And there are theoretical ways that you can see what should be the exchange phase and what you should get. And using those ideas, they can prove that you have anyonic excitations in these fields. Directly, you can measure the exchange phase by taking one electron around another. And you can, every time there is an extra anyon in this place, you can show that there is a phase change. And again, by measuring these phase changes, all of which are close to 1/3, they can show that this particular phase of matter has these anyonic excitations. Right? So these are direct, these were not, these kinds of experiments, like they're now talking about it, we couldn't have imagined them to be able to do it some 15, 20 years ago. You need fairly sophisticated ways to do these experiments. Both of these were done in 2020. And now there's been an explosion of topological materials. There are things called topological insulators, where the material behaves like an insulator, but on the surfaces of the material you have conducting states. So these are things which are called topological insulators. They have very different band structures from what are there in normal insulators. And now, because normal insulators, you wouldn't have anything in the middle. Normal conducting states, you'll have many of them in the middle. But here it's only the surface states which will conduct, but the interior states will be insulating. So these are all very unusual materials which have been found. And you can have wild semi-metal spin liquids. I mean, these are things that you might have heard if you've gone for talks in your places. Boré systems and bilayer graphene. Many of these things have flat bands, and in those flat bands you can get anyonic excitations. So the main points that I want to emphasize is there's been now, in the last 20-25 years, there's been a paradigm shift in the way of classifying phases. They're based on topology, or more correctly to say, interplay of topology with symmetries. Earlier it was just symmetries, Landau's theory. That was the way all phases of matter were classified. Now you need to introduce also topology in them to classify them. And anyons have entered mainstream condensed matter. Earlier they were considered very exotic, only a few theorists will be playing with them, and theorists can do anything, right? So they can always play with them, but now experimentalists are taking it very seriously because a lot of the experiments can be explained in terms of anyons. And it's important to understand that ideas from different fields has been used in the development of this field in the last several years. High energy physics, condensed matter physics, quantum information and entanglement ideas have also been used, and mathematics, knot theory, Chern-Simons theories and all that have been used. So let me just briefly give a brief interlude of my interests over the years. I worked on Chern-Simons field theories to start with, 1D quantum wires, bosonization, and Luttinger liquids, besides quantum Hall effect and anyons, and now I work on topological quantum matter. So yeah, let me just say I also worked on graphene and quantum Hall effect in graphene, and mainly all of this is a part of what is called topological quantum matter, topological insulators, and then on something which are called these Majorana modes, which are relevant for quantum information, right? So that's something which I now want to introduce as another this thing. But before I go on to introduce this non-abelian anyons, I thought I'll just briefly mention something which will be relevant to all of you as well, that you will have to go through some amount of gender-based struggles that in your career. And I was lucky that I didn't feel discrimination either at home. Our home was, they didn't discriminate between girls and boys, or in bachelor's in MSU, or even in IIT. Our class was special in that we had equal number of girls and boys, which was very unusual, 8 and 8. And the girls outperformed the boys, so we didn't really feel that there was a problem. There was a lot of sexism and gender bias in IITs. IITs are terrible at this, but it just happened that our class tended to be lucky. Right? So we didn't feel it. And the fact that we were oblivious probably helped. So I would tell all of you also that even if there are, just ignore it. To a great extent, that does help. And PhD and postdoc years were also fine. It was back in India as a faculty that you start feeling that people don't take you very seriously. And particularly young men and all who are close to you in age, who may be students and postdocs, they will definitely discriminate, or there will be other issues. It's not easy for a young woman physicist to be taken seriously, which is something which all of you as students will also probably feel, that many of your classmates may not take you seriously and so on. So you need hard work. And in my case, I had a particular problem that I was married to someone who became extremely famous. And so to compete, or not even to compete, to establish myself independent of him, it was a struggle. So which was one reason that it was better for me to switch my field away from high energy physics and move to condensed matter physics, which was a very good decision in the long run because I liked it much more. And it turned out to be very useful to have different perspectives in physics. And this is something I can tell you, life does improve as you get older because people do take you seriously. Once you have white hair, life is set. But you don't have to wait till you get white hair. I mean, Vandana will tell you, even with black hair, it's fine. Because you start having PhD students who you can mentor. My involvement in women in physics issues started in 2000s when I was asked to collate a questionnaire regarding women in physics and present it to an international working group. Because India at that time didn't have such data, and we were trying to get data between ourselves with people who knew each other. And surprisingly, at that time, most women, including me, said that there was no gender bias in India. And there was, we all thought, everybody said we have personal issues, but there's no problem with the system. And there was no gender bias at all. And no system. But then there was this International Union of Pure and Applied Physics conferences in women in physics, which started in 2002 and was continued every 3 years after that. I attended the first 2 or 3. I was part of the organization of the first one, and then I attended another couple. and then this brought together women in physics from all over the world. And then it brought us, at least in India, to the realization there was systematic discrimination all over the world. India was actually doing better than many other countries because we did not have the idea that girls should not take physics in school. That thing was, as far as we knew, not there. And most problems in India started later as postdocs, and mainly due to social responsibilities, family responsibilities. And then after moving to Allahabad and all, I realized also that it's not uniform even within India, right? I mean, in the beginning, a lot of the data we collected was from mainly more urban areas. But having lived in Allahabad, one knows that there's a lot of discrimination in different parts of India, even at school levels. Then their faculty positions are scarce. There's this two-body problem. You can't get two jobs in the same place. But I will still say, compared to our times, young women now, I think, are much more aware of sexism. There are more positions, and slowly the number of women in physics is increasing, but not fast enough, but it should increase even more. We now have, as Vandana said, a gender, in fact, she's been responsible for a lot of the changes that have been brought. So even she, single-handedly, she does many things. So it was formed by the Indian Physics Association in 2017. And now even every subject, like Ganit matter, high energy and all, have their own working groups in women in physics. They've initiated lecture series, and they work towards equity and inclusion in science and technology of women and other underrepresented groups. So that is the general idea that we want to do. There are these initiatives like, we have one for women in physics undergrads, first year BSc in ICTS. We just started 2-3 years ago. Vigyan Vidushi has been running for the last 7 years, I think. But permanent women faculty percentage is very low, particularly the elite institutions like TIFR and all will have very, very few. IISc and TIFR will have, I think, extremely few. But there have been successes. Rohini got the Padma Shri in, many of you must have heard of Rohini Godbole, and she got the Padma Shri in, and Aditi is the first person. She's from Harishchandra Research Institute, getting the Bhatnagar in, I think this was 2019, it says. And Urvashi Sinha got the Bhatnagar in 2023. So I wanted to also mention that there are success stories. And with this, I'll come to the last conceptual thing that I want to introduce, which is something called non-abelian anyons. I'll try to do this through pictures. I'll have some equations, but I won't go through that. I'll just try to do it through pictures. So this was a kind of non-abelian anyons which was introduced into a toy model by Kitaev. And the main importance of this, reason that this is an important concept, is because it can be used for fault-tolerant quantum computation. And essential idea is just that when there are degeneracies in the problem, that there are many states which have the same energy, then what can happen is when you exchange two particles, instead of getting a phase, you can actually get a matrix. Because you've seen many component wave functions, right? Like in the Dirac equation, or when you have spin degeneracy, there are two component wave functions. So if you have many component wave functions and you exchange them, then the components can also change. You can actually have a matrix, not just a phase when you exchange two particles. So such particles are called non-abelian anyons. And the simplest model for this, let me just go directly to the pictures. Every fermion can be written in terms of, say, two Majorana, what are called Majorana modes, right? Every fermion, if you may not, some of you are comfortable with second quantized notation, or may not be. So let's just do it in pictures. Then every fermion can be written in terms of two, you can think of them as made up of two particles. But by changing parameters in the theory, you can also go to another kind of phase where instead of these two particles making the fermion, these two particles are making the fermion. And this to this can be done by some kind of change of parameters in the theory, right? You can go from this picture to this picture. The difference between these two pictures is that in this picture there are two end Majoranas which are left free. So now you can think of putting these two end Majoranas in a box and either, putting a fermion in that box or not putting a fermion in that box. Those two things are actually degenerate. So that forms your degenerate subspace, right? What happens is that this was Kitaev, in fact, the model that he does is this is magic trick. He cuts the fermion and puts different parts of them at two ends. Normally a fermion, you can always cut it and think of it as two very close to each other. He managed to get a model where these two parts of the fermions can be separated and put at two different ends. And those are called the Majorana modes. And since no energy is required, they are called Majorana zero modes. The only important point that I want you to note is that this fermion state form, this Majorana zero modes, is these two modes can be far away from each other. It's something which is called non-local. So if I have an impurity at this end, it can't disturb the whole thing. If it's something which is very local, if you have a spin qubit, it's very easy to flip it, right? Any disorder can flip the qubit. If you think of these two spin states as your qubits, right? Whereas if you think of putting a fermion or not putting, the occupation of this long range state, it can't be easily disturbed. So that is the reason that you have this thing called topological protection for these states. So these are the states which are going to make your qubits. And so two pairs of them can make a two-level system. And what can happen is that you can think of two such fermions, so four Majoranas, you can prepare them and then you can exchange one Majorana from this with another Majorana from that, and that is what is a braid group, and that's a unitary transformation from one state to another. So some of you may have done some amount of quantum information or quantum qubits or heard about these qubits, right? What you have is qubits, then you have unitary gates which act on these qubits, and then you go to another state, right? So that you can do using these Majorana qubits. And because it's non-local, it's extremely stable. So that's why all the companies and so on are desperately trying to make this kind of they're looking for Majoranas. So this is the quest for Majoranas. There have been many, many papers, many of which have been withdrawn, not proven to be correct. The latest paper, has it finally been seen? There's a paper with about 127 authors from the Microsoft team with 35 graduate students, and they've done a combination of many experiments, and they see it in roughly half of their samples. And they're now very careful. They say passing the protocol indicates a high probability detection of a topological phase hosting Majorana zero modes. Right? They have not said, they don't say that we have found it. Earlier papers said it and had to withdraw it. So now they're careful. And this demonstration is a prerequisite for experiments involving fusion and braiding of Majorana zero modes. So this is Microsoft's Majorana 1. I don't know, again, this came in the news sometime ago, February 2025. They claimed is the world's first quantum processing unit with 8 topological qubits. And they intend to build a fault-tolerant quantum computer in years and not decades. But is this true or too good to be true? We have to wait, because nobody else has replicated it. Being a company, they have also not given all the details out. So until someone else replicates, the scientific community will not even believe that there exists such a thing. So I believe, I would like to believe, Majoranas have been seen, but the jury is out. There's no this thing yet. So let me end my section. What are the things? I wanted to just show this picture, that one of the things that I really liked is that, after many years, I went back to MS University, Baroda, where I did my undergraduate. And I didn't know, but I suddenly found my face up there with Venki Ramakrishnan, who's a Nobel laureate, Sam Pitroda. These are all the alumni from my university, which I didn't know, and then put it up. So it was fun to go. So that will be the real this thing, that both things that we value are when you go back to your home place and you get some recognition. As she already said, my major contribution to my field has been my students. I've had many PhD students, master's students, and I love mentoring students, visiting students also from various places. And I've learned as much from them as they have from me. And many of them are now in IITs and IISers. So now I don't take PhD students anymore, but I have worked with what I call my grand students. And then we come now to Anyon's future. So these, of course, are, just up in the air. There are these things called moire materials. I don't know if you've heard, graphene multilayers, right? For fractional quantum Hall samples needed ultra clean samples, very low temperatures, very high magnetic fields. These moire materials allow engineered fractionalized states. You can kind of design quantum materials, right? So can we engineer anyons rather than discover them? And you can also have these fractional churn insulators. I'm just coming from a conference in LTPI where they were saying that they have been able to do these kinds of things by using twisted transition metal, chalcodine, many possibilities. But all of these are now being explained in terms of the people's claim that they have anionic excitations. And you can do that. And beyond Majorana's also, you can have other kinds of non-abelian anyons, because even if you have Majorana's, you will not have universal topological quantum computation. You will need to get some gates which are not topological. And so, but you can have something like Fibonacci anyons, parafermions, they will give you more gates. Fibonacci anyons, in fact, can give rise to universal quantum computations. So the idea is to engineer materials which can have these quasi-particles, and then their exchanges can do quantum computation for us. That's the idea. So that is something which is going to be in the future. And again, as I said, the remarkable developments of the last 20 years is that many of these things, topological phases, you need quantum information, entanglement, high energy physics, Chern-Simons theories, topological field theories, mathematics, braid groups, knot theories, something called modular tensor categories. They've all merged in the study of these phases. And the progress is truly likely to be interdisciplinary, maybe with inputs from industry like Microsoft and all other places maybe you need. So the open questions: can non-abelian anyons be conclusively, unambiguously observed? There's a famous guy in the field called John Preskill. He bet with Jonathan Dowling in March 2020 for something which will be settled on March 2030. And but the stake is very small, pizza and beer, which means he's not too confident about it. I think even the one who's rooting for quantum computation is not too confident about it. We have to find out whether this can actually scale, can we engineer them, can topology survive disorder and temperature, what other new particles can emerge. So the future is yours, right? When anyons were proposed, they looked like a strange mathematical possibility. Today they connect topology, quantum matter, information and computation. So we don't know where the next breakthroughs will come. So you have to give us ideas about this. And the main takeaway points that I want you to take away from this lecture are that mathematics and abstract ideas can lead to new physics. So don't be worried about doing very theoretical stuff. They will still give rise to real physics as well. And even new technology, as we can see. And different fields of studies can cross-fertilize each other. So don't specialize too soon. So learn as many things as possible when you can. And the other thing you have to know is that scientific careers are non-linear. You'll have ups and downs. And the important thing is to be persistent. As she already said, I guess that this is something that most of the senior people tell you. You don't give up. You have to keep trying and something will come out. Okay, thanks for listening.
Thank you, Sumathi, for a wonderful carol. Nice topological carol, so must be really unique. And I really liked the way you actually sort of wove the story, both from the physics and as a woman physicist going back and forth. And because that's how things have gone and things have grown both ways. So it's very interesting. I'm sure you'd like some questions if there. Please, go ahead.
I'll be happy to answer.
Don't hesitate.
Is there any experimental evidence of abelian and non-abelian anyons?
Experimental evidence for abelian anyons is there, right? I already, that is in anyons present, right? These, I mean, to show you that these actually prove evidence, I'll have to do a little bit of theory and this thing, which I did not actually do over here. Essentially what is happening is that you have the edge states of the, you put various quantum point contacts over here, and you have these edge states of the fractional quantum Hall liquid, and they will tunnel through from one edge to the other edge, and depending on that tunneling, you can actually see whether there's no board. If an electron, if a quasi-electron, if an anyon comes from here and an anyon comes from here, you can check whether both of them will go in one, or if they were bosons, both would like to go in one. If they are fermions, if you bring an electron from here and let them collide, they will go in two different. That's called anti-bunching and bunching. And if you do the same experiment with these kinds of anyons, you will see that it's intermediate. The results that you get are neither for bunching or for anti-bunching, and they exactly match with what you would expect if they were 1/3 anyons for fractional quantum Hall effect 1/3. If it's another phase that you put in 2/5, then you'll see that the phase exactly matches with what you would expect. So anyons have been seen. And there's a second experiment also which sees anyons, which is this one, where what happens is that you are looking at the Aharonov-Bohm phase kind of thing here by studying these backscattering currents as a function of the area and the magnetic field. They've been plotted as a function of the area and magnetic field. When there's no anyon in the system, it will go like this. Each time that you change the backgate and there is one more anyon formed, you can show that there is a shift here. And the shift, by measuring the shift, you can show that the phase is exactly 1/3. So that is the way they show that this has quasi-particles which are exactly anyonic in the system.
And for non-abelian, can't we prove the same?
For non-abelian anyons, is what I said at the end, right? This
claim is there.
question is whether you believe. I mean, this is the experiment, right? They say that they have seen anyons, and they have even made a chip which has anyons, non-abelian anyons. That's the claim. The question is, I mean, I've looked at this, I haven't seen this, of course, I've looked at this paper, and there is convincing evidence, like from looking at the paper, that they can show what is called the gap closing, gap opening, many things which are needed. And they've also been able to show that at both ends of the wire, you simultaneously get Majoranas. These were all not shown in the first experiments. So these experiments seem to be convincing, but I'm not an experimentalist, I'm not this thing. So unless there's many other people who also say, who can repeat the experiment and show it, the community will not accept that there is. I mean, they have to do it. Many other groups have to do it besides one group.
Ma'am, I don't know if it's right to ask, but since this particle is a quasi-particle in 2D quantum systems, does it have a spin? Can we talk about assigning a spin to anyons?
Meaning, it will be, if it is useful in some context, it might be, but in these contexts where we are looking at it, it doesn't have part of the reason being that there is a high magnetic field, so it gets polarized. So it's equivalent to there is not having a spin. But you can, in the 2D, this thing, you can think of it as a fractional spin. And if you do that, then the spin statistics theorem is obeyed. You can think of it as having a fractional spin, just like a half integer spin. These will have things like some kind of number, which will be consistent with the spin statistics theorem with the statistic that they get, right? Like bosons have integer spin, fermions have half integer spin, and these will have intermediate spin.
All right now.
Yeah.
Ma'am, as we saw that in case of bosons and fermions, if we interchange the position of particles, and let's say after changing it twice, we can get the initial configuration. But in case of anyons, the history matters.
Yeah.
So are we saying that in the current state, like the current state is affected by the previous changes?
Yeah, I mean, the thing is, if you have a system of anyons, right, you have many quasi-particle excitations, then it does, yeah. What did you say exactly? That it is history. It matters. How you got there matters. Like, let me try to explain. Yeah. Where is this? Oh. This one, right? See, this has 1, 2, 3, 4. This also has 1, 2, 3, 4, right? But these two configurations are not exactly the same, right? If I just looked at the configuration as on the 2D sample, they will look the same. But how they came there matters, right? So the history matters, that's what you say. If you have multiple configurations, those are those unitary gates that you can do, and the entire history will matter.
Thank you.
We should also have some question from this side to have balance.
Ma'am, you mentioned that we get to see anyons in the fractional quantum Hall effect.
Yeah.
Nowadays, we talk about the quantum anomalous Hall effect. So, do we get to see anyons through that also?
At least, yeah, again, very recently, yes. I mean, I think, as I was saying, in today's conference, I was hearing all these things. But many of in quantum anomalous Hall effect, the anyons that are being talked about are still at the theory level. Whether experimentally they can prove that they are anionic excitations, I don't know. So the way that you explain what is now the quantum anomalous Hall effect and the things that are getting out of it, theory, definitely, a lot of the theory talks were on anyons and
Ma'am, in integer quantum Hall effect, you have shown that that peak curve you have shown. So can we say that when the electron density passes the Fermi level, we get that peaks, and when the electron density is not near any Fermi level, we get that plateau lines?
No, I mean, let me say what. This one, right?
No, the previous one.
Integer quantum Hall effect. What you're going to be changing is the magnetic field or the density of electrons, right? It's not that the Fermi level. Try to see how they say this. As you change the density of the particles, the point is that the conductance does not change. What you're plotting here is resistance or conductance, right? And you're plotting here the transverse resistance and the what is it called? Linear resistance, right? One is the transverse, one is in the same direction, and one of them gets quantized. The other one, whenever this is quantized, this is 0. So you're passing current like this, but you're not getting any resistance, right? So it's not to do with the Fermi levels of the system. You're changing as you're changing the Fermi level, you're getting a plateau. Is that what you're asking? Maybe I can explain it offline a little better.
Anyone else? Oh, okay, there is a question there. Yeah.
I wanted to ask if like the anyons had any special interactions with fundamental particles and whether it would lead to any new BSM signatures or something like that.
Any what signature?
BSM, beyond standard model.
Well, beyond standard model not possible because, I mean, of course, they're not in 3+1 dimensions, right? So you wouldn't get, it has to be inside a material. They're not free particles. So that way it will not really affect that way. But within the system itself, you could have anyon excitation. There are systems where you have E/3 anyons, 2E/3 anyons, and electrons. You can also ask about how will they interact with each other, but you can't ask with elementary particles.
I had this question that you mentioned about the phase change in non-abelian this thing. So what kind of phase change it is? Like, is it like UAB that you have mentioned?
Yeah.
So it's not
UAB is a unitary matrix.
Okay, so what kind it is
What I'm trying to say is the UAB, phase change, I meant e raised to I theta AB was a phase.
Yeah.
Now the phase itself is a matrix.
Yeah, but what kind of it to make it non-abelian? Like in we have SU2 and
This could be, yeah, if it depends on this unitary matrix. If this is a 2×2, if you have a 2 qubit, if the degeneracy is 2,
yeah.
right? If you have a degeneracy of 2, then this would be a SU2 matrix.
Okay.
Right? If you have a degeneracy of 3, it can be SU3 or U3 rather.
And how is Chern-Simons theory involved?
Chern-Simons theory is related to not only non-abelian but also to abelian. Okay. I mean, what you have is that there is this e raised to I theta, right? That what I was talking about is like attaching fluxes, right, to particles. That flux attachment can be done via Chern-Simons theory. I mean, it's like it's not a real magnetic field. If you're familiar with Chern-Simons theory, it's that epsilon mu nu alpha, a mu, d nu alpha, right? That is the kind of a field. In terms of normal gauge fields have -1/4 f mu nu, right?
I am not that aware, but yeah,
Meaning
I know it's
if it's a gauge field is an is a vector field,
yeah.
right? If you have a vector field, then there is in normal electromagnetism, you know what is minus
yeah.
1/4 f mu nu, right?
Yes.
So similarly, for the Chern-Simons theory, you can write down a particular term which is called the Chern-Simons field, and that will do the flux attachment. So the magnetic field, because normally you have electric and magnetic fields, and they are written, you know how they behave.
Yes.
For a Chern-Simons theory, what you find is that the charge itself and the vector field get related through this Chern-Simons theory.
Okay.
And you can also have it in the non-abelian version.
Okay.
So if they're non-abelian fields, then it's an SU2 or an SUN gauge field.
Yeah. Okay. And how is non-abelian this thing, anions, more effective than abelian anions? More significant, or what is the advantage of non-abelian?
Advantage, it's for quantum computation. You can't use,
okay.
I mean, abelian anyons you cannot directly use for quantum computation. In the non-abelian anyons, the thing that is happening is that because you are being able to make qubits which are non-local, right? Okay. That you cannot do with just abelian anyons.
Okay.
So you need degeneracies in the system, which will give rise to these multiple psi A, psi B kind of a thing, and then you need to separate the non-abelian portions of the thing to make a qubit.
Okay.
So if I don't see any more hands, so let's thank Sumathi for a wonderful talk and also sharing her journey with us. And she's very much around and she would like to interact with you people. Of course, she'll join you for dinner, but now also after the lecture, we can carry on some interaction. We would like one picture of you with all the students. Yeah. So maybe you can come down. Yeah. Can someone take photo from this side?
Where the picture is here? Or?
Yeah, you can just have it here. You can have a seat here and we'll just take it. You're going to sit ahead of Sumathi. You should come here.
Thank you. Thank you.
Very nice. Very nice. So you can feel free to interact with them.
So she's offering me to.
Oh, it's really, I know, I mean, it's been.
Here is better because it's AC, that's what it is. Yeah.